2 months and some days ago. So this is my first update/short talk to show you what's my main topic right now, what I've learned and what I've been working on, and what's next for the future. So the main topic is quantum machine learning. So I'm going to start by explaining what classical machine learning is, in particular a supervised learning task. So in this kind of task, learning tasks, we have some input data. The dimension of the input data corresponds to the number of features that describes the phenomenon which we want to classify. And to each data point, we assign a label that indicates the class of the data, the input data. So what we do is that we train our model so that it learns some map between the input data and the labels. That is called a feature map, and we do this by minimizing the sum cost function. So the idea is that if we feed our model, our trained model, new unseen data, it can correctly classify it. So in our case, we are interested in two models. One is neural networks, which are interconnected layers that we train to classify input data. And then we have kernel methods. What they do is that we have some feature space which we obtain with the feature map, and then in the feature space what this algorithm does is that it finds a hyperplane that maximizes the margin between classes to correctly classify them. So in quantum machine learning, the thing that changes is that the feature map is quantum. So what we do is that we take our classical data and we encode it into a quantum system, and then we measure a quantum state, and then we measure it to assign a label. So in our model, in Pablo's model, he proposes to combine quantum neural networks and quantum kernels to construct a thing called quantum neural kernel. So the quantum neural network we are using is a data re-uploading quantum neural network. In this case, we have a circuit that has as many layers as we want, and in each layer we encode our classical data with a unitary rotation and some other unitary rotation with some parameters that we want to optimize. These parameters, we optimize them by minimizing a cost function that we define as this. This is the fidelity between the state when we measure and the assigned label. So for a binary classification task where we have two labels, where y can be 0 or 1, the thing is that we map the qubit state into we encode the classical data into a point in the Bloch sphere, and then we measure the probability of the state. If the probability of being in the south hemisphere is bigger than the other one, we assign the corresponding label. So in quantum kernels are a bit more tricky to understand, but what we do is, as I said before, we want to find an optimal hyperplane that separates the points that maximizes the margins between the points in the Bloch sphere. So what we do basically is we construct something called a kernel matrix, and we do this with this calculation, where S is the embedding strategy, that in our case is the quantum neural data re-uploading network. Okay, and so we feed this matrix to an algorithm called supervector machine, and it finds the optimal hyperplane. So why we are doing this quantum machine learning stuff? We want to take advantage of quantum phenomena as entanglement to see if we can improve machine learning algorithms, classical machine learning algorithms, with these quantum phenomena. So what Pablo did to take advantage of this is to construct a bit more difficult algorithm. So we start by training a single qubit quantum neural network. So in this training, we find a set of optimal parameters, theta star. So with these parameters, we can build a neural quantum kernel by replicating this exact circuit as many times as we want and entangle each circuit. And with this, we can find the optimal hyperplane that separates the classes. Or we can add a second qubit by entangle both qubits in each layer with other variational parameters that we want to optimize. But when we train this 2-qubit quantum neural network, we are going to use these first optimal parameters that we found here and set the initial entanglement parameters to 0, so the entanglement grows bit by bit to improve the classification task. And then with this, we can construct a neural quantum kernel with as many qubits as we want. So far, Pablo has been using qubits for classification tasks such as satellite classification, satellite image classification, and neutrino classification, and it worked really great. But the thing is that we can only encode 3 features in qubits because the dimension of the SU algebra is 3. So if we manage to extend qubits to Qudits, so a more general levels, we can encode more features, which is a more realistic model of machine learning. So the first thing to do was to try to simulate Qudits. So far, Pablo was using PennyLane, which only allows you to work with qubits and qubits. So the first thing to do was to get rid of PennyLane and find some other tool to do this. One of the first options was QForge. This is a library that was released like a month and a half ago. It's a library for Qudit simulation. It was the guys, I talked to these guys and they were super nice. They explained me the library, so I don't know. I really liked it, but I didn't end up using it because I found some small limitations to implement Pablo's model. But I wanted to show it, so if someone is interested, I learned quite a bit of this. So I was looking for another thing, and I found this other paper where they implement the data reuploading in Qudits using the Gell-Mann matrices, and only using PyTorch, which is the main library that is used for machine learning in Python. So I took what they did, and I implemented Pablo's model with this in Qudits. So to show you an easy example, this is a 3-class classification task. So we have points in a plane, and they are divided in 3 classes. So we have 2 features in 3 classes. If we train a 1-qubit quantum neural network with this, we can reach a test accuracy of 93.8%. Then, if we do a 2 Qtrit quantum neural network, the accuracy increases by 98%. But then, if you implement the kernel to this training, for a 1 Qtrit, the test accuracy is 98.7%, and for a 2 Qtrit quantum neural kernel, the accuracy is 99%, which is super high. This is, of course, a super simple data set. The results are not as good with others, but this is the one I had the most information about. But so far it's working. So the next thing to do is to generalize the problem to any dimension and try on more, adding more Qtrits and different encoding strategies. Of course, working with multiple Qtrits and testing on more interesting data. So, yeah, thank you.
Thank you. Be the first topic is topic. So,
yeah, thank you very much. I think I think why are they trying to go to Qudits? Why do you want to use Qudits?
Qudits, okay, the encoding strategies are unitary rotations. So in qubits, the rotation is a rotation in the block sphere. So it has three parameters, right? So if the input data has 4 dimensions, is a 4 vector, you can't encode this data in qubits. So you need a Qtrit that can encode 8, up to 8.
What's the advantage that you expect to have by using a Qtrit instead of 2 qubits?
Okay, this is something I'm still learning, but the thing is that if you add more qubits, it doesn't scale well, and also the measurement.
From what I understand, it doesn't scale well because you have many qubits, you end up having these kind of training problems, the problems that you cannot train.
Sorry, what?
If you increase the number of qubits, the problem is that training that circuit becomes more difficult.
Right, and I don't know, but I don't know if you can encode different data points in different qubits.
But qubit contains the qubit, 2 qubits contain the space of the qubit, right? So somehow you should be able to do that.
Yeah, with the entanglement between them, but
I mean, easy advantage is using qubits instead of qubits, but there was the motivation to use them.
okay. Yeah, I think it's the scaling thing, right?
let's see on the operation to pass.
Okay.
I mean, it is interesting.
No. Yes. So if you have a qubit that I mentioned before, you have this universal operations to be faster in the sense of one of the layers to be related because you have to be able to generate a picture in meters in the subspace. Okay. Not the whole application is one. So from a mathematical point of view, there is no difference in how qubit that I mentioned before. You can generate a picture in meters. Advantage of qubits to be that in order to generate a single meter, faster you have access.
Yeah, and I think adding more qubits brings problems to the cost function parent plateau.
Yeah, but that could be the dimension. So if you have an equivalent dimension,
Okay.
And it's not more complicated because if you have several qubits, you can measure like all the qubits, but if you have a qubit, you can make one measurement.
It's also one of the games. So you can perform an integral measurement in because after the end of the day, you're going to measure only but if you want to perform global unitaries, several qubits, you need them. The global unit and global unit. So the idea is not qubits because they are qubits, it's because it's the way in which we can increase the number of features. And qubit is a general way, a general we can use it. And we compose qubits that probably will be found. We don't have access in general. Qubits,
Measure that maybe is going to increase the number of qubits that the dimension of the qubits because qubits probably have 16 dimensions. I don't know. But if you're doing it like qubits have 20 qubits that qubit between 2 to the 20.
the greater than is also in simulation, right? So if you're simulating qubits, you can increase the dimension by one. If you're simulating qubits, you can increase twice. So
space also increases the size of the matrix. Dimension of the qubit
okay.
also, you mentioned the cost function of infidelity. Is there a specific reason of choosing infidelity as a cost function or
The cost function?
yes.
Yeah, this one is what they use for this data loading construction of quantum neural networks.
So
There are many options, but this one is the most used.
yeah, but then you can know the final state of the
Sorry, what?
for fidelity, we need to know the target state you want to achieve.
Yeah.
So, in case you know the state for every case, target state.
I mean, when we train the model, we know the state that we want to obtain at the end for each class.
You are choosing 0 for one class, 1 for the
Yeah. So if we input data at and y equal to 0, you assign it to the 0 state of the qubit. So you already have this information.
You can also make the developing videos. Or you can choose something that is accurate itself. So it's one if it's in the right plane, and it's still it's in the other. Well, yeah, they were around 1 minute. Questions or comments?
I have one comment because you are using some packets to simulate this, and I got to know that people in Innsbruck who has a setup on Traptallions, they are going to publish a simulator for their system with their gate set and everything.
Okay.
So when I got it, I will give it to you.
Okay. Yeah. Thank you. Yeah, because I create everything with PyTorch, with Tensor PyTorch. But yeah, sometimes it can be, I mean, if I scale this to a 10 level Qudit,
Yeah, no, it's
I,
impossible. Because I mean, in any case, you will be limited by the space of the Hilbert space. You cannot escape that. So you will only be able to simulate 2-3 Qudits, but yeah, at least they will have a noise model.
okay, thank you.
It's one of those. You can increase the resolution and any level qubit. So that does it mean that you don't need in principle multiple number of qubits, which is the case for qubit, right? So you can just increase the number of levels and
Just keep one Qudit.
one qubit.
Yeah. I mean, it's an
Can
option.
show you.
Then let's say, Camila, thank you very much.